All right, so thank you very much for the kind introduction. I'm thrilled to be here, and much like Robert, I regret we're not now in Argentina. You know, since Silvia and Daniel sent the invitation, I have started learning Spanish. So I want to take a minute and say gracias Silvia y Daniel por la invitación. Es un placer ser parte de este evento. So. What I'm going to speak today about is a topic that is at the intersection of harmonic analysis, partial differential equations, and geometric measure theory, areas in which the analysis school in South America has a distinguished tradition and has had exceptional contributions. This is joint work with Irina and Marius Mitrea from Baylor University. Let me start just by, reminding quickly everyone, something we teach our, undergraduate students in advanced calculus, the classical divergence theorem, so I'm going to consider, just for simplicity, a bounded domain in R2. I'm going to take n equals 2 for simplicity, a bounded C1 domain with outward uninormal nu, and a vector field F, which is of class C1 all the way to the boundary, so on the closure of the domain omega. Then the integral over the domain omega of the divergence of F with respect to X is integral on the boundary of the inner product between the uninormal vector and the vector field nu and the vector field F with respect to the surface measure. Okay. I would like to take a second here and walk you through the main ideas of the proof. So, via a localization argument, one can reduce matters to considering omega to be the upper graph of a C1 function phi defined from R into R. And as such, the boundary of the domain omega can be realized as the graph of phi. So it's the collection of points x phi of x with x running over the set of real numbers. The vector field F has two components, F1 and F2, which are of class C1 with bounded support. Okay. Then, using Fubini's theorem, we're going to write the left-hand side in the divergence formula, namely the integral over the domain omega of the divergence of F with respect to X, as integral over R, integral from 0 to infinity, of the divergence. We're looking here at partial 1 F1 plus partial 2 F2, and here we're looking at a point in the domain omega, which is the upper graph of the function phi. So points in there look as x phi of x plus t, where x runs over the reals, over the set of real numbers, and t runs from 0 to infinity. Okay. Moving on, a simple application of chain rule allows us to express partial 1 F1 as the difference between these two differentials, dx of F1 evaluated at the point x phi of x plus t minus the differential with respect to t of phi prime F1. Okay. And while partial to F2 is simply the differential with respect to t of F2 evaluated at the point x phi of x plus t. So this is, just a simple application of the chain rule. And we're going to have to integrate the divergence. So the sum of these two terms, so it amounts to these three terms contribution, 1, 2, and 3. All right. However, the integral over the real line of the first term, the differential with respect to x of F1 with respect to x is simply going to be 0 due to the fundamental theorem of calculus and the support considerations the support conditions that we have for the vector field F. So as such, when we're integrating now the divergence, we're simply left with the contributions of these terms. So we have the contribution of this term and the contribution of this term, since the other one contributes 0. So we're going to have to, we're employing Fubini here, and we have integral from R and integral from 0 to infinity, the integral of the first term, and then plus the integral of the second term. Again, things are set up in such a way that we can easily apply now, we're integrating here two differentials with respect to t, and the first integration happens to be with respect to t. So the fundamental theorem of calculus, applies easily, and taking into account the support conditions on the vector field F allows us to express the sum as integral over R of phi prime evaluated at x, f1 of x phi of x minus f2 x phi of x. So this is what the left-hand side in the divergence formula is. I'm gonna spend a minute to try to explain what the right-hand side is. So if we look at points on the boundary, these are the points on the graph of the function phi. These are points of the type x phi of x, where x runs over the set of real over the set of real numbers. Then we differentiate with respect to x in order to find the tangent direction, and then we take a vector that is perpendicular on that and normalize it appropriately in order to get the formula that we have here for the outward uninormal vector. So nu of x is going to turn out to be phi prime evaluated at x minus 1 over the length of this vector. Okay. So then when we're gonna have to integrate now, we're gonna go back here and look at the left-hand side in the divergence formula. We're looking at the inner product between the uninormal vector and the vector field f. The vector field f has components f1 and f2. Now we have the uninormal vector written here. So it's going to be scalar product with the expression that we got. And the integration with respect to the surface measure now is in 2 dimensions is simply the arc length measure. And as we know from our calculus classes, that simply amounts to introducing the square root of 1 plus phi prime square dx here instead of the surface measure. All right, so the square roots cancel one, this square root cancel the one in the bottom, and taking the inner product here leads exactly to the expression that we computed earlier. Okay, so that's a quick proof of the classical divergence formula. I would like to point out here that what really made this argument possible is our ability to write the domain omega as the set theoretic product between its boundary and 0 in the set of in the positive semi-axis, the interval 0 infinity. So there is a distinguished vertical direction, that allows us to employ Fubini's theorem. And then I would like to point this out because I'm going to be interested in versions of the divergence formula that hold in domains that lack this particular geometrical structure. I'm going to be interested in versions of the divergence formula in domains where the boundary is not even locally the graph of a function. So all these elementary arguments that I have reminded everyone about, fail to apply. So just to add a little bit of context, historical context here, I would like to point out that it is remarkable that after more than 3 centuries, the divergence formula, remains an active area of research, but this is a demand-driven subject. Progress in a certain area of mathematics often requires yet a new, more potent version of the divergence theorem, which can accommodate certain specific features. Our work here is motivated and shaped from the very outset by potential applications to elliptic PDEs in non-smooth domains. So we'd like to have the ability to integrate by parts, to apply the divergence formula in domains that are very irregular. Needless to say, the divergence theorem is one of the most basic tools in analysis, and ongoing efforts for deriving optimal versions of this result have shaped the field of geometric measure theory. So let me go further, and now walk you through some geometric and analytic assumptions. What is reasonable to, I would like to look for, in the measure this is possible, I would like to look for a sharp version of the divergence theorem, all right? So I would like to impose minimal geometric assumptions on the domain omega and minimal analytic assumptions on the vector field F that makes the divergence formula hold. And I'm going to walk you through a series of examples that are going to illustrate some of the necessity for some of the requirements that we're going to have in the main theorem. So in trying to identify geometric assumptions for the domain omega such that the divergence formula holds, let me start with the following problem. Suppose that we have an open set, and suppose omega, let's call it omega, and let's assume that we have a locally finite Borel measure mu on the boundary of the domain omega, not necessarily the surface measure, just a locally finite Borel measure. And let's assume that there exists a vector defined on the boundary of the domain omega, taking values in the unit sphere in Rn, define mu almost everywhere, such that this parallel version of the divergence theorem holds. So n is not necessarily the uninormal vector, but it's a unitary vector. Mu is not necessarily the surface measure, but it's a finite Borel measure. And this divergence-like formula holds for any C infinity vector field which is compactly supported in Rn. Okay? Let's say what just this mere assumption that that we have this formula, the existence of this measure and of this boundary vector n implies on the domain omega. So let's look at the supremum over all vector fields which are C infinity compactly supported, with the support included in a given, let's say, we're gonna fix some compact set K, and we're gonna take that the support of all these vector fields are in the compact K. And we're gonna assume that, the vector field F in L infinity, is controlled by 1, okay? And we're looking here at the absolute value of the left-hand side of our formula, okay? Because of the assumptions that we made on the measure mu and then on the support conditions of the vector field F, by assuming that this equality holds, then the left-hand side can be simply controlled by the measure of the trace of the compact set on the boundary of the domain omega, because the vector n is bounded by 1, and this is all that we obtain. If we, at this point, drop the middle term, and this is going to be strictly less than infinity because mu is a locally finite Borel measure and then K is a compact set, we obtain that this supremum is a finite one. For those familiar with the language of geometric measure theory, you're going to recognize here the definition of a set of locally finite perimeter. So the moral that I would like you to take out of this quick analysis is that if the divergence theorem is okay for nice vector fields, then the domain omega necessarily is going to be of locally finite perimeter, okay? How about the converse implication? Does omega of locally finite perimeter implies the divergence formula hold, implies that the divergence formula is valid for nice vector fields? So in order to answer this, this is a much more difficult question, and then in order to state here a famous result, I will need a little bit more notation. Here, Hn minus 1 is the n minus 1 dimensional Hausdorff measure in Rn, and by partial star omega, so I adorn the partial here with a star, I denote the measure theoretic boundary of the domain omega, which consists of points of positive density. So these are points on the domain omega, which, heuristically, at any scale, bite a significant amount both out of the domain and out of the complement of the domain. So here you see the formal definition. Okay. And by sigma, we're going to denote to be the restriction of the n-1 dimensional Hausdorff measure in Rn to the boundary of the domain omega. The answer to the question that I asked, whether a set of locally finite perimeter would be enough in order to ensure a divergence theorem for nice vector fields, has been answered positively by Di Giorgi and Federer in their famous version of the divergence theorem. So here, if omega is a set in Rn of locally finite perimeter, then for agn minus 1, almost every point on the geometric measure theoretical boundary, there exists a measure theoretic outward uninormal vector nu, and the divergence formula holds for any vector field F, which is C1 compactly supported in Rn. Okay, note here that the integration over the boundary, takes place over the geometric measure theoretical boundary, where we have a concept of uninormal vector. The Di Giorgi-Federer's divergence theorem is sharp from the point of view of the geometry, but the assumption of the vector field F being of class C1 compactly supported in Rn is too strong, especially from the point of view of partial differential equations. Many times we need to integrate vector fields, on which, such strong smoothness assumptions are lacking. Going further, let me, try to address, some analytical conditions on the vector field F. I'm going to try to impose analytical conditions on the vector field F, which are, essentially a bare minimum in order to make sense of the divergence formula. So I'm going to start by asking that the vector field F is locally integrable, so I can talk about the divergence in a sense of distributions. Okay. I'm going to ask that the divergence of F is L1, so that I can talk about the left-hand side in the divergence formula here. Okay. I need to make sense of F restricted to the boundary, and here, I'm going to consider this in the non-tangential pointwise sense. This is a natural point of view based on applications coming from complex analysis, harmonic analysis, PDEs, going back all the way to FAT2. So I'm going to assume that, so I'm going to now adorn the restriction to the boundary with the letters N and T here, by standing for non-tangential. I'm going to say that, I'm going to assume that F restricted non-tangentially to the boundary at the point X is the limit as Y approaches X, where Y stays in the non-tangential region generated by the point X of F of Y. And I'm going to assume that this is true for for sigma almost every point on the boundary, where the non-tangential region is described here. If the domain omega were an upper half space and the point X would be a point on the boundary, gamma of X would simply be a straight upright cone with vertex at X, and aperture, determined explicitly in terms of this coefficient 2 here. Okay. All right. So now let me walk you through some examples. So let me consider now the situation where the domain omega is just the punctured unit ball. Okay, so that's the domain omega in here. And I'm considering here the vector field F of X, which is X over absolute value of X to the power N, where N is the dimension of the Euclidean space that we're in. This is easily recognizable, in a first year course in PDEs. This is simply, the gradient of the fundamental solution for the Laplacian. So F, because I have eliminated 0 at the point where this vector field has a singularity, is C infinity. The divergence of the gradient is simply going to be the Laplacian of the fundamental solution, and the point 0 is not considered. So there we have a harmonic function. As such, the divergence of F is 0 in the domain omega. Nu dot F, nu simply on the ball on the boundary of So the domain omega, the topological boundary consists both of the circle and of the point. However, the geometric measure theoretical boundary points of positive density consists only of the boundary of the circle, because the point 0, if we take small ball center at 0, this bite nothing out of the complement. So the center of the ball is not a point of positive density. This doesn't belong to the geometric measure theoretical boundary. So here nu dot F, because we get X dot with itself and we're on the boundary of the unit balls, it's simply being equal to 1. But the divergence, so the divergence, the integral of the divergence is simply going to be 0, while the integral here in the right-hand side is going to be a strictly positive number. So there is something, that cannot, so one of the geometric assumptions that we're going to impose, is to eliminate pathological cases like this, so the point 0 does not have enough boundary mass. So to fix this, we're going to ask that the boundary of the domain, the topological boundary of the domain, behaves like an n-1 dimensional set with respect to the Hausdorff measure. So we're going to assume that the boundary of the domain omega is all-force regular in the following sense, that there exists C bigger than 0 such that for any point on the boundary of the domain omega, and for any R between 0 and the diameter of omega, the surface measure of surface balls of radius R are comparable to R to the power n-1. If the boundary of the domain omega is all-force regular, then the domain omega is of locally finite perimeter. The geometric measure theoretical outward uninormal vector nu in the sense of the Georgian Federer exists. So let me consider now another example. Okay. I take the unit ball and I eliminate from it the entire segment xn equals 0 in the entire hyperplane xn equals 0. Okay, I consider the same vector field. So at this point, the geometry measure theoretical boundary consists both of the circle and of this line segment, if we're into dimensions. So all-force regularity is satisfied in this situation. However, all the properties that I mentioned before about the vector field, continue to hold. So the left-hand side is 0 and the right-hand side is strictly bigger than 0. And the problem that, that occurs in this situation is that the set theoretic difference between the topological boundary and the geometric measure theoretical boundary now has strictly positive surface measure because it's the measure of this entire segment. So what we're going to do to prevent this further, we're going to make this assumption. We're going to ask that the n-1 Hausdorff measure in Rn of the set theoretic difference between the topological boundary and the geometric measure theoretical boundary is 0. Okay. And I just want to, I'm not going to walk you through the technical definitions. I'm just going to show you a couple of domains, BM1 domains, open sets in Rn with the property that near every boundary point, they are the upper graph of some function phi, which is locally integrable with a gradient of phi belonging to the space of bounded mean oscillations. This is a domain that would satisfy this type of condition that I imposed. NTA domains with the all-force regular boundary for those that are familiar with these terms. And just to show you that, this type of analysis takes you out of the class of Lipschitz domains, let me start with the following zigzag function. So we consider the following Lipschitz function phi, which has the following graph, zigzag lines of slopes plus and minus 3 on dyadic intervals. And we're going to consider the following by Lipschitz homeomorphism. F of x and y from, f acting from R2 into itself is x phi of x plus y. And we're going to look at the image of the domain omega, which is this triangle, through the by Lipschitz homeomorphism f. What this is going to do is going to smash the triangle, so this is a smashed cone. This is not a Lipschitz domain because of the behavior that, because of the behavior of the domain near the boundary point 0, okay? However, this is an all-force regular domain. It satisfies the geometric condition that I've just imposed earlier. Also, a two-brick domain. If you take two bricks and place them one after another, this is a domain that fails to be a Lipschitz domain. However, it satisfies, the all-force regularity condition that I have invoked. And finally, a last analytic assumption. I'm going to look here at the hemisphere, the hemisphere in Rn. Okay, so this is 0. And I'm taking the same vector field. What happens now in the case of the hemisphere, nu dot f is going to remain 1 on the round piece of the topological boundary, and it's simply going to be 0 on the flat piece because nu is perpendicular on x in here. So the left-hand side is still going to be 0. And then again, on the right-hand side, we're going to have a strictly positive contribution due to the portion where the inner product between nu and the vector field f is equal to 1. So the divergence theorem still fails to hold. The problem here is that even though nu dot f exists sigma almost everywhere on the topological boundary and belongs to L1, the divergence formula fails because the vector field f is too singular. The geometry of the domain omega hides the singularity of f when taking this inner product. And thus, we need to control how the vector field itself behaves near the boundary of the domain, not just how good ultimately the inner product is. So the type of conditions that we're going to be imposing here is asking for the non-tangential maximal operator, which is taking the supremum of f of y over y belonging to the non-tangential region with generated by the boundary point x. We're going to ask that this non-tangential vector, this non-tangential maximal function is in L1. And here is the statement of the divergence theorem that I advertised. These are the conditions that I said. F is in L1 log, so that I can talk about the divergence. The non-tangential maximal function is in L1 because of the last counterexample. The geometrical assumptions on the domain are that the domain is an all-force regular domain motivated by the counterexamples that I've shown you earlier. And we're assuming that the non-tangential trace exists sigma almost everywhere and the divergence is integrable. Under such conditions, you know, the divergence formula holds. I want to say, that, this is part of general theme. This is part of a much bigger project in which we were looking at the divergence theorem as a tool to solve elliptic PDEs in non-smooth domains. And this is part of a 5-volume research monograph that is going to appear soon in Springer Verlag called Geometric Harmonic Analysis. A summary article on the divergence theorem has appeared last fall in the notices. And, over the years, we have been successful, in applying these, these versions of this tool, to problems arising in complex analysis, dealing with Cauchy integrals, Calderon projectors, the multidimensional Riemann-Hilbert problem, and applications to PDEs, to the Hodge Laplacian, you can have versions of this theorem on manifolds. You can deal with second order boundary value problems and higher order boundary value problems in non-smooth domains. And with this, I would like to thank everyone for your attention.